Hey everyone, here is your video on formal derivatives. So I just wanted to remind you all, last time that you watched you watched a video on the intro to derivative where we imagined throwing something up in the air, like the grapefruit, and then it landed on the ground. And that was all about approximating or finding an average rate of change, which was the average velocity in this case. And for our graph, we had position and we had time. And whenever we thought of slope here, we imagined slope as being some kind of velocity. Like the secant line slope would be average velocity, the tangent line slope would be instantaneous velocity. So that's all fine. You can do a position and time graph. But what we want to do right now is generalize this method a little bit more so it doesn't have to be time here and velocity here. We want to generalize this for any kind of rate of change, because in calculus, we want to find more than just velocity rate of change, because again, you can really do the rate of change of anything that is changing, like cost, profit, stocks, height, things moving in our universe, really anything. So we're going to generalize this. So we're actually going to do 3 different sketches here. So apologies in advance if you do not enjoy drawing graphs, but you really need to practice drawing the graph so you can see what's happening here. All right, so the first graph I fully drew for you, and the other ones I'm going to draw with you. So we're going to generalize this graph right here, and we're going to just say x and f of x. And what we're going to do in this first visual is we have x naught, and x naught is where we really want to find the instantaneous rate of change. And I'm not necessarily going to call it velocity now, it's just a general instantaneous rate of change. And then this is going to be our value x1, which, because remember, we need 2 points to find slope. So this is our other x value that we use. And we want these 2 points to be really close together. And right now in the drawing, they don't look that close together because it's really hard to make this drawing look neat if your 2 points are super, super close together. So mine are not that close together. And here I have the y value that goes with this x value and f of x1, which goes with x1. Okay, so what's happening here is we're going to write a couple things down for our first graph. So take a minute and finish drawing this sketch here, and then I'm going to scroll down here. So our main goal in this video is to find an exact value of the instantaneous rate of change. That's going to be called the derivative. The whole goal of unit 2 and 3 in calculus is to find a derivative. Again, rate of change at a single instant. We don't want to have to just approximate anymore. We want to get exact. So what we have here is the secant line slope, which is the average rate of change. So average rate of change is secant line slope. And we know how to write slope. It's change in y over change in x. So what I have here is the change in my y values, and here are the change in my x values. So once your diagram's done, why don't you fill this out here? Again, the slope of the secant line right here. Change in y, that would be f of x1 minus f of x naught. That's this difference right here. And then change in x, that would be x1 minus x naught. So that's just regular old slope of a secant line, and this has a name here. It's called the difference quotient. It's called a difference quotient because you're subtracting things, which is difference, and a quotient because you're dividing 2 things here. And again, difference quotient in this case gives you the average rate of change. Okay, so we really wanted the instantaneous rate of change at x naught, x sub 0. We used x sub 1 to find a good estimate for it. So what we want to do is we want to make this drawing look a little bit more like the formal definition of a derivative that you would see in a textbook. So instead of x naught and x1, like that is a fine way to write it. But what you're going to see in a textbook uses a more. So we're going to draw this one more time here. And this one I'll draw with you. And again, follow along as I draw this. I really want the instantaneous rate of change at A. Anytime you see A in one of these secant line drawings, A is where you want the rate of change. However, I need 2 points to get a slope, so I'm going to settle here and pick another point. We're going to ultimately make X approach A, but whenever I draw it, they're not going to be extremely close yet. So I'm going to go up, straight up till you hit the curve, and go over, and that is f of A. And this, what I'm doing now, is just to help you make an accurate landing point for the y values. Sometimes people do like a really inaccurate, they'll put like f of x up here or something when it's not even close to where it should be. So those little dash lines I'm drawing just help you be a little bit more accurate. And then if you recall in class, if I haven't given it to you yet, I'm going to give you a tiny little slip of paper that has, I think, 4 graphs on it showing the secant line turning into the tangent line after we viewed it on Desmos, like in motion. So I'm going to use P and Q here just so we have points we can talk about. So our point Q is going to get closer to point P as X gets closer to A, which means our secant line is going to get close to our tangent line. So what I'm going to do here is draw my secant line, and I'm going to do my best here drawing a secant line, and I want to make my secant line, I'm just doing different colors here, but if you don't have different colors, just do your best. So my secant line is going to go between P and Q, and again, do your best making this look like a straight line. It is C. Oh, that's even worse. All right, so this is my secant line, and I'm going to label that. Remember, what we actually want, though, is the slope of the tangent line, because the slope of the tangent line is the instantaneous rate of change. And I'm going to do my best to make a tangent line. So I want this one to be green so it stands out. Whoop. So my tangent line is just going to graze the curve at, oh, that is a solid tangent line right there. Okay. So I'm going to call this thing tangent. It's grazing the curve at one single point. That is what I actually want. So as X gets closer to A, the secant line rotates to the tangent line. So make sure you're keeping up here with the drawing. Let's talk about visuals here. So what I have is this little triangle. And I need my y values and my x values, like the changes in those. So this is your change in y. Your change in y is f of x minus f of a. Woo. And here is your change in x. Your change in x is going to be x minus a in this case. And what I want to do here is write a secant line slope for these variables and these letters that I used. So it's going to be change in y over change in x. F of x minus f of a, all over x minus a. And remember, this secant line point goes through points P and Q. P and Q. I should probably write goes. This goes through points P and Q. So this looks really, really similar to this one over here, just slightly different letter choices. So before I go to the next slide here, I just want to emphasize one more time that mathematicians want the slope of the tangent line. And my x value is going to need to get very, very close to my a value, like infinitely close to the a value, so that the secant line actually turns into the tangent line. Make sure you're all good on that. I'm going to go to the next screen here. All right, can you jot this down here? These are just some comments for you to refer back to. These are important notes. So what, again, we really want instantaneous rate of change at x equals a. That is same thing as asking for the slope of the tangent line at x equals a. We need to approximate it using another x value with point Q. Remember, point Q was right here. Point P is wherever a was, where I really want the tangent line. So as your x value approaches a, or as q approaches p, secant line gets closer and closer to tangent lines. That means the slope of the secant line approaches the slope of the tangent lines whenever x goes to a. And you don't need to write this thing down here, this little bit, but that's just saying, like, the visual, that little slip that you tape down, that's basically what is happening there. And we also did this on Desmos whenever you animated it. So let's talk about a couple things here. I want you to label these 3 things here. All right, f of x minus f of a, all over x minus a. Hey, we just wrote that. That is your secant line slope. Secant line slope. And I didn't really give myself a lot of room here, did I? So I'm going to try and edit this on the fly. Get down there. Okay, cool. Now, also, I don't know why my computer couldn't handle putting x approaches a here, because it looks weird all the way over there. Anyway, what I'm doing now is I'm doing a limit of the secant line slopes. Limit of secant line slopes. And then, whoa, what is going on this side here? What is that notation? If you haven't seen this notation before, there's a F with a little tick mark A. F tick mark A, the way you say that is F prime of A. We're going to say that so many times this year. F prime of A is the derivative of F at A. You could also call it F prime of X, like very soon, instead of saying F prime of A, a lot of times you're just going to say F prime of X. But anyway, F prime of A, what this is the derivative. Anytime you see F prime of A, you're being asked to find the derivative. So what this means is the derivative is equal to the limit of the slopes of the secant lines. That's what's actually happening here. So your secant lines get closer and closer and closer to your tangent line. That limit, whatever the secant line slopes approach, that's your tangent line slope. All right, cool. So make sure that is all written down, and let's take a look at one more graph. This is the last one you need to draw. Can you jot this down for yourself as well here? That I'm going to talk about in a minute, because check it out. There is another way to write the formal definition of the derivative. People, I don't know if you realize how amazing this is, but this right here is the derivative of any function at point A. Like, you know, you have the power now to find the derivative of anything. This is one way to get the formal definition. There is another way, which I'm going to put a 2 here. There is another way to write the formal definition of the derivative. And I don't know what I was thinking with derivative. Okay, there's another way to write it. So let me make a note here. There's another way to write the difference quotient using h. Okay, so you might be wondering, what is h? We're going to call h the distance between A and the other point on the x-axis that you have to use to approximate the derivative or the tangent line. So here's how you draw this one, okay? I'm drawing my function. That is what is in red. This is your f of x. I have my point A, which is where you want the derivative. As always, that's where you want the tangent line. Here, instead of calling it x or x1, I'm going to call it A plus h, because the distance between those two is h. And what's going to happen, again, is A plus h is going to approach A. So let's go ahead and write this down here. If that's A, that's f of A. If this is A plus h, and I can still call these points P and Q if we want to be consistent here, then this right here is f, of A plus h. Do your best writing that down as neatly as you can. And I'm going to make my little triangles here. So again, keep up with me. We have this and we have this. Those represent the rate of change. So this is my delta y. And wait, I don't even have a tangent line drawn yet. Let me draw a tangent line, because we can't find a slope if we don't even have a tangent line to find a slope of. So I'm settling for now, people, okay? We're going to settle and just do a secant line, just so we have a visual. All right, so here's the secant line. And what I'm doing here is changing y, which was f of A plus h minus f of A. And then my change in x is A plus A plus h minus A. Wait a second, what is A plus h minus A? Doesn't that just cancel? Yeah, that's just h. So my delta x is h, okay? So we can write our slope here as change in y over change in x. Recall on the previous slide, the way we wrote it was f of x minus f of A all over x minus A, like you just wrote that down on the other slide. The way we're going to write it here is my change in y was f of A plus h minus f of A all over change in x, which is just h, because the a's canceled. So that means, can we write a formal definition of a derivative? Well, we said that the derivative is a limit of the secant line slope. So let's try and translate that to here. So I'm going to have a limit of my secant line slopes, f of A plus h minus f of A all over h. But hold on, what has to happen here in order to go from a secant line to, are you ready? Let's make a tangent line. Let's see how good I can do this. No. Okay, sorry. 1 second. Do your best to do a tangent line while I fumble around here. All right, that's just going to have to do. It's my tangent line. Well, in this slide, what had to happen, in this slide, what had to happen is that x had to approach A, which is why you did a limit as x approached a. But what's happening here? A plus h has to approach a. Well, what's really happening is that h has to approach 0. If h approaches 0, that means a plus h approaches a. Okay, so pause for a minute and listen to that again if you need to. That's critical here. When h is small, like basically 0, the slope of the secant line is going to be basically identical to the slope of the tangent line. That's when h goes to 0. Here is another vocab word for you, and that is the vocab word differentiable. So we already talked about like f prime of a and how f prime of a is the slope of the tangent line. If this limit exists, and when I say the limit, I mean like this limit, meaning you can find a derivative, we're going to say a function is differentiable. So that we have difference quotient, you have differentiable, you have your formal definitions of derivatives. There's a lot of notation and vocab coming your way right now. So differentiable means you can do the derivative at a certain point. All right, cool. I just need to show you one example and then you'll be good to go for class. We have these limits here, right? So let's go ahead and actually try using this limit definition and try finding an exact derivative. That means I'm no longer doing like f of 2 minus f of 2.001 all over 2 minus 2.001 and getting an estimate. Like we don't need to do that numerical estimate anymore. You're going to get an exact derivative function. I'm going to do it with a quadratic, but again, you could do this with really any, well, I shouldn't say any. You can do the method I'm going to do right now with a lot of functions. So I'm going to do it with a parabola, and then you can mimic this with any other function I give you. Remember, x squared plus 5 is just a basic parabola shifted up. That's not a parabola. Shifted up 5 units, like that. Okay, so I want to find the general derivative. I guess I should say the derivative function, because I'm not asking you to find like an actual numeric slope, like, oh, the slope is 2 or something. I want you to find the whole derivative function. I'm just going to call it f prime of x. And like I said in class, this is kind of like the initiation period where you got to do the long way before you do the shortcut way, because you need to understand where all these things are coming from. The long way helps you see how the shortcut way works. All right, I think you're going to love doing this. Let's see. I'm going to use this way. Now, remember I just said there was 2 ways to do a formal derivative. There was way 1 here, and then way 2 here. We're going to do the second way first, and then very soon you're going to try the other way. You get the same answer either way, and you're going to probably find you prefer one of them more than others, but we got to try first so you can make that decision, like which one you prefer more. All right, so I'm going to try and use some highlighting here to make this easy to follow. And let me not erase important things here. Okay, I'm going to find f of x plus h first. And then what I'm going to do is I'm going to subtract f of x. Well, I already know what f of x is. F of x is this. And then I'm going to divide by h. And there's going to be obviously some algebra involved. Now, what we're going to see is that the calculus is not difficult. It's the algebra that can get tricky when you do these. Even if you look at this one and you're like, oh, that's not bad. They can get a little crazy, especially when you get to like a cubic, not just a quadratic. So f of x plus h, what on earth does that even mean? That means you're going to take f of x, and instead of x, you're going to put x plus h. So instead of x squared plus 5, I'm going to do x plus h squared plus 5. So I'm going to plug that in here. And we've already hopefully emphasized this a lot. You keep writing limit until you plug in. So I'm going to take f of x plus h, which I just found. X plus h squared plus 5. Okay, that was this one right here. And that one's going to go right here. And then I'm going to subtract f of x. Well, what was f of x? X squared plus 5. Hold on. I need to show I'm subtracting the whole thing, and I just wrote down 2 terms. So I'm going to put parentheses there because we're going to distribute that negative, right? No one's going to forget that. So there we go. Color coding is good to go. All over h. Now, I better not see anyone in class doing this. If you do, I'm going to freak out. X plus h quantity squared is not x squared plus h squared. Okay? We are going to FOIL that out, so that means x plus h, so x squared plus 2xh plus h squared. Okay, I'm still doing a limit. Keep up with me here. If you want to try doing this without like looking up, I compare. You can obviously do that. X squared plus 2xh plus h squared. That was this. I still have a plus 5. Then I have minus, let's distribute this negative, minus x squared minus 5 all over h. I'm going to do one less color coding here, and then I won't really be able to color code anymore because you know that you will have done this correctly if a lot of things cancel out. Basically, anything without an h should be canceling, okay? So let's look really carefully here. I have x squared minus x squared. I have 5 minus 5. The only things left have h's in them, which is great. So I have the limit as h goes to 0, 2xh plus h squared all over h. All right. If I tried plugging 0 in for h right now, I will get 0 over 0, which is indeterminate form, which means do more work. Let's see if I can factor and cancel, because I'm not going to stop at 0 over 0. And what can I factor? Well, if both terms have an h, you can factor that out. So I'm going to factor an h out of the numerator. That leaves me with 2x plus h all over that h in the denominator. Yes, here we go. I'm still writing limit. You better be writing limit still too. 2x plus h. Okay, you are used to plugging in something for x whenever you do a limit. Like at this point, it'd be like the limit as x approaches something. Now you have the limit as h goes to 0. So I'm going to plug in for h. Don't get tripped up there. And I'm going to plug 0 in. So, oh my gosh, we're done. 2x. So what on earth is this? This is the derivative function, which is the slope of the tangent line at any x value. And if I said, hey, what's the derivative like at x equals 1, then you would plug 1 into here and get 2. So at 1, your slope is 2. And if I was like, hey, what's the derivative at x equals negative 3, you'd expect something much steeper and probably negative. So if you plug negative 3 in here, your slope's negative 6, which is steeper and negative. So isn't that amazing? We're going to practice in class, and you're going to get really fluent with this. So, cool. That is all. I'll see you in class.